Applications of integrals in geometry. In mathematics, integral geometry is the theory of measures on a geometrical space, invariant under the symmetric group of that space. In more recent times, the meaning has been broadened to include a view of invariant transformations from the space of functions on one geometrical space to the space of functions on another geometrical space. Such transformations often take the form of integral transforms, such as the Radon transform and its generalizations. Integral geometry as such first emerged as an attempt to refine certain statements of geometric probability theory. The early work of Louis Santalo and Wilhelm Blasch was in this connection. It follows from the classic theorem of Crofton expressing the length of a plane curve as an expectation of the number of intersections with a random line. Here the word random must be interpreted as subject to correct symmetric considerations. There is a sample space of lines, one on which the affine group of the plane acts. A probability measure is sought on this space invariant under the symmetric group. If, as in this case, we can find a unique such invariant measure that solves the problem of formulating accurately what random line means, and expectations become integrals with respect to that measure. The theory of invariant measures with respect to continuous groups of transformations of a space onto itself, on sets consisting of submanifolds of the space, for example, lines, planes, geodesics, and convex surfaces. In other words, manifolds preserving their type under the transformation in questions. Integral geometry has been constructed for various spaces, primarily Euclidean, projective, and homogeneous spaces. In order to introduce an invariant measures, one tries to begin with a function, depending on the coordinates of the space under consideration, whose integral over some region of the space is not changed under any continuous coordinate transformation belonging to a specified Lie group. This requires finding an integral invariant of the Lie group. The latter can be found as a solution to the system of partial differential equations.
Where is the required integral invariant is a point of the space, having dimension or the coefficient of the infinitesimal transformation of the group, and is the number of parameters of the transformation. Of great significance in integral geometry are measurable Lie groups, that is, groups that admit one and only one invariant, up to a constant factor. In particular, simple transitive groups are of this type. The following problem in integral geometry consists of determining a measure on a set of manifolds that preserve their type under some groups of continuous transformations. The measure is given by the integral. In integral geometry on the Euclidean plane, one usually considers only one type of continuous transformation, namely the group of motions. For a set of points, the integral invariant is the unit. For a set of lines, it is again the unit if one selects for the parameters of the line and of its normal equation. The length of an arbitrary curve is equal to, where is the number of intersections of a straight line with the curve, and the integration is carried out over the set of straight lines intersecting the curve. The measure of a set of straight lines intersecting two convex figures is equal to the difference of the lengths of the cross-common tangent lines of the oval and outer common tangent lines. Outer common tangent lines cross common tangent lines. The measure of the set of straight lines dividing two ovals is equal to the length of the cross common tangent lines minus the sum of the lengths of the contours of the ovals. The measure of a set of pairs of points is determined as where are the parameters of the normal equation of the straight line passing through the points and are the distances along this straight line from the points to the point on the line having minimal distance from the origin. Integral geometry originated with problems on geometrical probability and convex bodies. Its later developments have proved to be useful in several fields, ranging from pure mathematics, measure theory, continuous groups, to technical and applied disciplines, pattern recognition, seriology. The book is a systematic exposition of the theory and a compilation of the main results in the field. The volume can be used to complement courses on the differential geometry, Lie groups, or probability or differential geometry. It is ideal both as reference and for those wishing to enter the field.
Problem number 1. Find the integral of x cubed over x squared plus 2x plus 5 dx. The rational function we want to integrate here is not proper. So there, first thing we must do is long division. This tells us that x cubed over x squared plus 2x plus 5 is equal to x minus 2 minus x minus 10 over x squared plus 2x plus 5. So our main work is to integrate the new proper fraction. The integral of x minus 10 over x squared plus 2x plus 5 dx is equal to the integral of x minus 10 over x squared plus 2x plus 1 plus 4 dx. The integral of x minus 10 over x plus 1 squared plus 4 dx. The integral of u minus 11 over u squared plus 4 du is from u is equal to x plus 1, du is equals to dx, u minus 11 is equals to x minus 10. 1/2 and the integral of 2u over u squared plus 4 du minus 11, the integral of du over u squared plus 4. 1/2 and the quantity of u squared plus 4 minus 11 over 2 arctangent to u over 2 plus c. The ln of square root of x squared plus 2x plus 5 minus 11 over 2 arctan quantity of x plus 1 over 2 plus c is the final answer. Putting it all together, we have the integral of x cubed over x squared plus 2x plus 5 dx is equal to the x squared over 2 minus 2x minus the ln of square root of x squared plus 2x plus 5 plus 11 over 2 arctangent to the quantity of x plus 1 over 2 plus c. Number 2. Find the integral of the logarithm of x over x minus 3 squared times dx with a maxima of 2 and minima of 1. Start with the integration by parts. Let u is equals to ln x and the derivative of x minus 3 raised to negative 2 dx. Then du is equals to dx over x and v is equals to minus quantity of x minus 3 raised to negative 1. So, the integral of the logarithm ln of x over x minus 3 squared with a maxima of 2 and 1 dx is equals to the negative ln x over x minus 3 with a maxima of 2, 1 plus the integral of the logarithm dx over x quantity x minus 3 with a maxima of 2 and a minima of 1. To compute this integral, we find the partial fraction decomposition of the integral. 1 over x quantity of x minus 3 is equals to a over x plus b over x minus 3 is equals to a quantity of x minus 3 plus bx over x quantity of x minus 3 is equal to a quantity of x minus 3 plus bx is equals to 1. Setting x is equals to 3, we find that 3b is equals to 1, so b is equals to 1/3. Setting x is equal to 0, we find that negative 3a is equal to 1, so a is equals to negative 1/3. So, the integral of the logarithm x is equals to x minus 3 squared times dx with a minima. The integral of the logarithm ln x over x minus 3 squared times dx as 2 being the maxima and 1 as the minima is equals to the quantity of minus ln x over x minus 3 plus 1 over 3 ln the absolute value of x minus 2 minus 1 over 3 ln the absolute value of x as 2 being the maxima and 1 being the minima is equal to ln 2 over 2 over 3 plus ln 1 over 1 minus 3 plus 1 over 3 ln the absolute value of 2 minus 3 minus 1 over 3 ln 2 minus 1 over 3 ln the absolute value of 1 over 3 minus 1 over 3 ln 1 is equals to ln 1 minus ln 2 over 3 minus ln 2 over 3 is equals to ln 2 over 3 since ln 1 is equals to 0. This connection with representation theory is one of principal stimuli for the modern development of integral geometry. But integral geometry also has essential connection with many other areas of mathematics. Some such as areas are symplectic geometry, multidimensional complex analysis, algebraic analysis, nonlinear differential equation, and aspects of Riemannian geometry. The Radon transform and its variation are the mathematical base of computer tomography.